gravitational waves from this source compact binary coalescences to do cosmological inference. And the property that I'll focus on is the fact that these compact binary coalescences are standard sirens. And so what does that mean? Well, so I talked about how the intrinsic parameters are encoded in the gravitational waveform. So intrinsic refers to like the masses and the spins of the black holes and the neutron stars. Gravitational waves also encode extrinsic parameters. So things like the distance to the source, the orientation, like where is the orbital plane relative to the plane of our detectors, and the sky position of the merger. And so this property that gravitational waves encode distance is extremely special for an astrophysical source. And that's why we call them standard sirens. And the way that works is that we have the gravitational wave strain. So right, this is this dimensionless change in distance. And that is equal to the redshifted chirp mass to the 5/3 power of the gravitational wave. So bigger black holes are louder intrinsically than smaller black holes and neutron stars. Also the frequency, because the strain changes during the frequency. These other angular parameters, like the phase of the gravitational wave and the position and orientation. So some function of that. And then the important thing is that this is all inversely proportional to the luminosity distance of the source. And so the gravitational waves directly encode this luminosity distance because the redshifted chirp mass, which kind of scale the intrinsic loudness of the gravitational wave, that we can read off from the frequency evolution. So just from seeing the frequencies of the gravitational wave, we know how intrinsically loud that source is. And so how loud it appears in our detector is just a function of how far away it is, and also like where it is on the sky and stuff. And so but the thing is that we can get the luminosity distance, but we actually can't get the redshift because the redshift is completely degenerate with the mass. Gravity is scale free, and so there's no way of knowing if when we see that something merges at a frequency of 40 hertz, is that, which is relatively low frequency, is that like low frequency source something that is very massive and like very massive in the source frame, or does it just look very massive because it's a lighter merger that is happening far away, and it's just those frequencies are just getting cosmologically redshifted. Right, so we can get luminosity distances, but not redshifts. Let's talk a bit more about those distance measurements. So we can observe mergers out to several gigaparsecs with our current detectors at our current sensitivities. This is just showing all the detections that are public. So far, the luminosity distance in the log base 10 of the megaparsec. So this is 10, this is 100 megaparsecs versus the signal to noise ratio. So this is like how loud the gravitational wave appears in our detectors, related to the amplitude of the waveform. And so you can see both the distribution of where those mergers tend to be in distance. So out to like several gigaparsec, really, up to like maybe 10 gigaparsecs up here. And also the typical distance uncertainties. The fractional distance uncertainties tend to be like 20% at 1 sigma, or like 50-ish% at 90% credibility. That gets better for things that have very loud signal to noise ratio. There's also kind of this trend where the things that are closest by tend to have the loudest signal to noise ratio, but that's degenerate with the masses. I'll get to this later, but there's also this important degeneracy to keep in mind, which is the distance versus inclination. So, right, the amplitude of the gravitational waves scales inversely proportional to the distance, but there were also those angular terms. And so one of the important ones is the compact binary coalescence, the orbital plane of that, is it edge on or face on or face off to us. So the face on and face off configurations are going to have the loudest gravitational waves because gravitational waves are beamed in the plane of the orbit, whereas the edge on are the quietest ones. So there's this degeneracy between, okay, the source looked kind of quiet. Was it face on and far away, or was it close by and edge on? And that's just this degeneracy that you see here between distance and inclination, where you can actually see that this is the difference between face on and face off. And we actually can distinguish that a little bit because of the polarization of the gravitational waves. So that's kind of cool, but again, there's still this degeneracy. Okay, and then in order to do cosmography, we want to essentially build this redshift distance relation. So we get the distances from the gravitational waves, but how do we get the redshifts? And of course, the reason we want to do this is because this distance redshift relation depends on this Hubble parameter h of z, which carries information about, like in our cosmological model, about the matter density, the dark energy density, the dark energy equation of state, all these things that we don't really know that well because we don't actually understand also what they are. And so so one thing we can hope to do with gravitational waves is to build this Hubble relation between redshift and distance. And the local slope of this is the Hubble constant, or h of z equals 0. And so we get the distances from gravitational waves, but we don't get the redshift from gravitational waves because they're degenerate with the masses. And so the first thing we might think is we can maybe get the redshift from the galaxy that the merger happened in, because these gravitational wave mergers are these probably these stellar remnants that are crashing with each other. Stars live inside galaxies. These objects probably live inside galaxies. Galaxies have measurable redshifts. And so let's just look at what the host galaxy of the merger is and learn its redshift. And then the problem is, can we actually localize a gravitational wave merger to its host galaxies? So like gravitational waves are super weird. Like we get the distances directly from the waveform, which is very strange for an astrophysical source. But we can actually localize them way less well than most things where we find with a telescope. And so the way that we measure sky position from gravitational waves is mainly with triangulation using the observed time delays between detectors. So when does the signal hit one detector, one LIGO versus the other LIGO versus Virgo, for example. And so right, with a time delay between two detectors, we get a ring on the sky, the width of which is just the timing precision. And so this is like the constant time delay ring. And for like that given time delay, if we have another detector, then we can get another ring, and then they can intersect at like 2 points. And then if we have a fourth detector, things improve even more because then there's only 1 point where they can intersect. So here are examples of some gravitational wave localizations from like the first few detections. And so in our very first observing run, we only had 2 detectors operating, the 2 LIGO detectors. And so all of these events that were detected at that time were just these essentially rings on the sky, like these rings that you see here. We don't have the full ring because we do have some more information than just the time delay in the signal, but it's basically a big ring on the sky. And so, right, there's more than one galaxy in that ring. When we have 3 detectors, so this was our first event where Virgo was also observing back in 2017. And so that is a much tighter localization on the sky because we now added that 3rd detector. And so here's just a sense of what those sky localizations are. Again, this is the log of the sky localization in square degrees. So this is 10 square degrees, and this is 100 square degrees. And then again, it scales approximately inversely proportionally to the signal to noise ratio. So the very loudest events which have signal to noise ratio like 30, this is our loudest event of the published ones, the binary neutron star merger, and well, that has the tightest localization for also because Virgo was online. But we have never gotten below like 10 square degree localizations. You can also see the difference that having 3 detectors versus 2 detectors make. So this is actually the events from our ongoing observing run, which aren't published yet, but we released the sky localizations as part of the low latency updates. And so you can see that for the first part of our 4th observing run, it was only 2 detectors, Virgo was offline. The sky localizations tend to be like 1,000 square degrees or more. And then when Virgo does come online in the second part of our 4th observing run, we have events that are actually localized to better than 100 square degrees, which is still a big chunk of the sky, but it's better than 10,000 square degrees. So there's that. So we actually get some more events in our 4th observing run that are localized to like a few tens of square degrees. That still corresponds to a lot of host galaxies in a typical gravitational wave localization volume. Something that I learned when I first started doing this is that there are a lot of galaxies in the universe. And so here's a plot from this paper by Xinyu Chen and Daniel Holtz from 2016, which shows the cumulative distribution as a function of the localization in both sky area and distance. So this is the 90% co-moving volume localization. And then here's the expected number of galaxies at that localization, assuming a galaxy density of roughly 1 per 100 cubic megaparsecs. And so you can see that for the bulk of events, binary neutron stars, relatively low mass binary black hole mergers, and the higher mass binary black hole mergers. So for the binary neutron stars, most events would tend to have like 100 or more gravitation or host galaxies potential host galaxies in that localization volume. For the heaviest black holes, which tend to be more poorly localized just because they're further away. And so that 20% distance uncertainty corresponds to a larger like physical distance. They tend to have like orders of magnitude more potential host galaxies in their localization volume. But there is a tail to very well localized events which have maybe only 1 host galaxy in the localization volume. And again, this assumes like 3 detectors operating at their planned sensitivities. So the loudest events with 3 detectors, 4 detectors would be even better, would maybe be localized to just 100 cubic megaparsecs and would just have 1 host galaxy. And then we can get the redshift from that host galaxy. But some mergers, we can be very lucky and actually have another clue to what the host galaxy is because we see an electromagnetic counterpart. And so this applies to like binary neutron star mergers, possibly some neutron star black hole mergers, where this is a cartoon back from 2012. So at the time, it was just a prediction of what might happen when two neutron stars merge. And so you could have this GRB along the axis of the initial orbital angular momentum, this very beamed emission of gamma rays. And then more isotropically, you could have a kilonova optical counterpart. You can have the afterglow of the jet, possibly a kilonova afterglow as well. And so there's a slew of electromagnetic counterparts. At the time of 2012, it was just potentially associated with binary neutron star mergers. We did actually see this once for our first and only multi-messenger binary neutron star event. And so here is a fun illustration, but it's based on the observations that we saw of that binary neutron star merger followed by the jet and then the kilonova and all that fun stuff. I don't have time to go into the details of all this electromagnetic emission, although it is really cool and taught us a ton about like how the heaviest elements in our universe are made, the origin of these gamma ray bursts, which is very exciting. But for the purpose of cosmology, this was still very exciting, but for a much smaller detail, which has allowed for the identification of the host galaxy. And so you can see in this plot the initial like low latency localization by LIGO and Virgo was these in green. So this and this arc. And then from the gamma ray bursts, there was some localization. It's kind of hard to localize things if all you have is a gamma ray burst, but that is narrowed down to here with Fermi, GBM, and integral together was this region. And then people were able, well, this didn't actually help the gravitational wave localization very much, but I guess it ruled out this part. And so people could point their telescopes and target this high probability region and actually find like a little flash in the sky, which was the kilonova. And that flash in the sky, which you can see here, was associated with this host galaxy, which is this big blob. And so telescopes have small, when you point a telescope, you aren't looking at 10,000 square degrees at once. So when you find it, you also find the host galaxy. And so that allowed for this host galaxy identification. The host galaxy is called NGC 4993. So when we do have counterparts, if we find the counterpart, we also find the host galaxy. And so we know the redshift of that source, regardless of the initial sky localization of the gravitational wave. Although having the gravitational wave somewhat well localized makes it possible to find the electromagnetic counterpart in the first place, especially if if you're looking for something in the optical, like a kilonova, where you have to point a telescope at it. So this happened once, and so we had the redshift associated with the distance, and we could make our Hubble diagram from that one source. Tomorrow I'll go into more detail about like the statistical formalism and some of the subtle details that actually went into this, but for the most part, is pretty straightforward, right? You now have a redshift that you inferred from the host galaxy. That's this vertical bar here, is that redshift. The reason it's not like, it is a spectroscopic redshift. So the redshift of that host galaxy is very well measured, but we want to correct it for any like peculiar motions and look at the Hubble flow velocity, which I'll talk more about tomorrow, but that's why this isn't like a dot. There is some uncertainty to the Hubble velocity. And then the distance from the gravitational waves of this one binary neutron star event, GW170817, it's 40 megaparsecs with some uncertainty there. And so you draw a line through it, which is essentially what this is, with some more detail I'll go into tomorrow. Oh, it's fine. And so the slope of that line is the Hubble constant. And so here's the posterior we get on the Hubble constant measurement from this event in blue. So we inferred it to be roughly 70 plus 12 minus 8 kilometer per second per megaparsec. It has this long tail in this direction because of the distance inclination degeneracy. So the distance we infer from the gravitational wave is degenerate with the inclination, and that causes it to have a long tail. And therefore the Hubble constant also has this tail in the opposite direction. And then just for comparison here, this is from our 2017 paper. For comparison is the best Planck measurement and best Hughes measurement at that time. And you can see these don't agree with each other because they're very well measured, and this is like the Hubble tension. And the gravitational wave measurement is very poorly measured relative to this, but it's just one event. So it, of course, agrees with both of them. But the hope is that we can narrow this down and eventually get to an independent measurement that is just as good as other ways we have of measuring the Hubble constant. And yeah.
I was curious, how much would a fourth gravitational wave detect?
How much would a fourth detector improve your constraint?
Improve this constraint? So not very much. It does help a little bit to have more detectors to get our distances. So this constraint is driven entirely, there's a little bit of contribution to the uncertainty of like the peculiar velocity of the host galaxy, which is what gives us the redshift. On the gravitational wave side, the only uncertainty is the distance uncertainty, which is driven by the unknown inclination of the source. Having a fourth detector could help us a little bit, like maybe like at the few % level, to better nail down the polarization of the gravitational waves, and basically the difference between like face on and face off, for example, is like whether the gravitational wave is like the binary is moving clockwise or counterclockwise. And so having more detectors can help us a bit with like the polarization measurements that go into getting the distance down precisely, but not very much. The thing that really helps on the gravitational wave side is just more events to get down the distance. Having a fourth detector would help a lot when it comes to the sky localization, both because, especially like on average, because you not only increase the amount of time where you have 3 detectors online at once, like each detector, even when it's on, it's only in lock like 80% of the time at best. So you increase the chance that any given gravitational wave event is observed by at least 3 detectors, which you really need in order to get a blob on the sky versus a ring on the sky. And then it also helps in like when you have 4 detectors, those arcs corresponding to equal time delays will always just converge to like 1 point. So yeah, for sky localization, it helps a lot. it would maybe have helped like find the counterpart faster, or in the cases where we don't have counterparts. So there's another question back there.
Are you working using LIGO, the low light detectors, so my question is, are we using for run 4, are we running LIGO plus Virgo plus Cogra, or is Cogra not yet part of that detector? Because in that case, you'd have your 4 detectors.
Yeah, so that's right. That's a good question. We do have 4 detectors technically, and Cogra has like joined the observing runs, but if you remember like an earlier slide I showed with the sensitivities of the detectors, the Cogra detector is like orders of magnitude less sensitive than the LIGO and Virgo detectors. So even if it's online, it wouldn't observe. It's not the sensitivity where it could detect any of these sources. So it doesn't really help yet.
In the model of the kilonova that was shown earlier, it's not spherically symmetrical. So does the fact that we saw the kilonova help knock down the inclination angle degeneracy at all, or?
That's a great question. And I will talk more about this tomorrow. But yeah, you can see here. So the topic of electromagnetic counterparts is super interesting, and especially thinking about how they help with like a cosmology standard siren measurement. The kilonova is, for the most part, expected to be isotropic-ish. So you can try to model, like, we think that like how much blue versus red kilonova it is does vary based on whether you're looking edge on or face on. You can try to model the kilonova. That's much harder to get an inclination from. What I'll show tomorrow is getting a measurement from the jet, because the fact that we actually did see a jet, sort of, I mean, we definitely were not looking down the barrel of a jet because it was way too weak for that. But we do have constraints that we're probably looking like just at the edge of where the gamma rays are. And that does give us an independent measure of inclination outside of gravitational waves. And so I'll show that tomorrow. But yeah, that's a really good question. Okay, maybe one more question.
And this might be anticipating where you're going next with the rest of the talk, but I'm curious approximately how many more localized to a galaxy compact binary coalescences would you need to get an uncertainty on the Hubble parameter comparable to the CMB or supernova measurements? Is it order like tens or hundreds?
Yeah, that is a good question. I will get a bit to this later, but just to give you a quick answer now, if we have the host galaxy, the scaling of the Hubble constant goes roughly at 15% over square root number of events. So if we have 100 events, we'll get to 1.5%. We first did those calculations. This is in a paper with Xinyu Chen and Daniel Holtz. We first did that in 2017, where we had one event really early on. And so it seemed like we would have 100 events within the decade. It's now like 8 years later, and we still only have that one event. So I'm going to talk about other ways we can get the Hubble constant without necessarily having unique host galaxies. But yeah, that's where we're at. Okay, cool. So let me move on and talk about some of those other methods. So again, what we're trying to do is to assign redshifts to gravitational wave distances. I talked about how we can do that if we have a counterpart where we just identify the host galaxy. If we don't have a counterpart, we can still just look at what are the possible galaxies based on the gravitational wave localization that are consistent with hosting this event and use that galaxy catalog as a prior on the possible redshifts that those events come from. That's often called like the statistical dark siren method. We might have an astrophysical redshift prior where we kind of know like merger rate tends to follow star formation rate. And so maybe our mergers tend to come from like some redshift, like redshift 2 or higher redshift. So that's kind of another thing we can do. We can do a cross correlation with galaxies, which is similar to the galaxy catalog approach, but more general, where we can assume that like both galaxies and gravitational wave events are tracing large scale structure in some way. And the gravitational wave events live in distance space and the galaxies live in redshift space. So we can do that cross correlation. We can use the source frame mass distribution. So we can use actually gravitational wave only approach, which I'll explain more. And we can also use tides in binary neutron star waveforms, which is similar to using the source frame mass distribution. But the idea there is that if you have a signature in the gravitational waveform that is telling you that is like at a fixed source frame frequency, you can use the redshifted frequencies that we measure to simultaneously infer redshift and the distance that we always infer. So the idea there is that like the masses and redshift are completely degenerate in the waveform. But if you have like tides in binary neutron star, that adds something that's no longer like scale invariant that corresponds to something, some fixed scale in the source frame, like the radius of a neutron star, which you can then infer the redshift from the redshifted frequencies. So I'll talk a bit about some of these methods. We often split these into 3 categories, which you can think about like as 3 flavors of standard sirens. And I don't know, flavors just makes me think of ice cream. Also, it's like summer and there's a lot of good ice cream places. So right, you can think of like 2 scoops of ice cream, if that makes you happy. So, okay, the 3 flavors that I will talk about for the rest of today and then also tomorrow are the bright standard sirens. So that's when we have a counterpart that gives us a unique host galaxy. The dark sirens, when we just use some statistical distribution of redshift, so we don't have a unique redshift, but we marginalize over possible redshifts of possible host galaxies, for example. Spectral sirens, which is when we have like features in the source frame mass distribution. So for the rest of today, I'll just give an introduction to all of these, and then I'll go into more detail tomorrow. So for bright sirens, that's when we have an electromagnetic counterpart and a host galaxy redshift. The only unambiguous example we have so far is that binary neutron star event GW170817, where we had the gamma rays and the kilonova and the afterglow in the radio. So it was like the whole electromagnetic range and gravitational waves. It was super awesome. But that's the one that we have so far. And so I already talked about how that gave us this Hubble constant measurement. And yeah, in addition to this, there is a claimed association of a binary black hole event called GW190521 with an AGN disk flare. So the idea there is that so we think that binary neutron stars, we know that binary neutron stars can have electromagnetic counterparts. Probably some neutron star black holes can also have electromagnetic counterparts. For binary black holes, we don't think they have counterparts for the most part because they are black holes and they're not made out of anything. But the idea is that you can have some binary black holes that merge in the accretion disk of an active galactic nucleus, for example. So you have this like big accretion disk, very dense gas around a supermassive black hole at a galactic center. And you can have stellar mass black holes that merge in that very gas-rich environment. And as they merge, the gravitational waves are emitted asymmetrically, and there's this recoil kick of the stellar mass binary black hole inside this very dense gas. And so the black holes moving very quickly, they can get these very large, like thousands of kilometer per second kicks, moving in this very dense gas can shock the gas and create this bright flare in the accretion disk. This is a possible electromagnetic counterpart you could have to a binary black hole event that would help you then localize to a host galaxy and get the redshift. The problem is that it's very hard to have an unambiguous association for a single event because AGNs are notoriously very difficult to model and they do weird stuff all the time. So they're like always becoming bright and modeling like the normal variability of an AGN versus like having a binary black hole merger inside an AGN is difficult to do. But this is something that like people continue to look for, especially because we just haven't been, the neutron stars haven't been merging as at higher rate as we originally inferred. And so this could be like a promising direction, at least statistically, to try to understand and help us find host galaxies to black hole events also. But okay, if we don't have counterparts, then we're just left with all of the galaxies inside the gravitational wave localization volume, and they could all be hosts of the gravitational wave event. So I'll quickly walk us through an example of using this catalog method. And that's from this paper from 2019, where we just, again, used our favorite binary neutron star event GW170817, which is, in addition to having a counterpart, it is our best localized event. So it was localized to 16 square degrees and on the sky, and it was relatively close by, only 40 megaparsecs. And so we can actually just look at all the galaxies in that volume, pretend that we don't know what the host galaxy is, and just use every galaxy as a possible host. And so the colors of all these different crosses are potential galaxies that are within this localization region. And these are their redshifts here. And so we can just marginalize over the possible redshift using that. And so, right, this is a lot of what I said. But yeah, there are around 400 galaxies here within some redshift prior. So we're looking at 40 megaparsecs with some uncertainty. But if we don't know the Hubble constant, we don't know what redshift range that corresponds to. So we have to look at a fairly wider range of redshifts to encompass like our prior on the Hubble constant. And so that's why these redshifts go down to 0.005 and up to 0.045. And so we can marginalize over all these host galaxies. There are 400 galaxies in the mix of galaxy catalogs that we used for this analysis that are all compiled in this catalog called the GLADE catalog, which we use a lot for gravitational wave cosmology. Also like the people who manage that catalog are in the LIGO-Virgo-Cogra collaboration. But anyway, the thing is that there's large scale structure, and so that kind of saves the day because even though there are 400 galaxies, they mostly belong to a single group which you can kind of see on the sky, but that group contains NGC 4993, which we're pretending we don't know is the right host galaxy, but secretly we do know that it's the right one because we found the counterpart there. And so if we just marginalize over those host galaxies, that's what's shown here. We get this, so let me just explain this plot first. This is the posterior on the Hubble constant. In the pink dotted dashed line is the posterior if we know the right host galaxy. It's here, it's slightly, it's peaked at like 76, which is slightly different than the analysis I showed you before. That's just because that's not an important difference. We're just using like a slightly different posterior for reasons that are not important. But the thing to compare to is the counterpart one with the one where we don't know the host galaxy, and so we just marginalize over everything. There are different choices you have to make when you do that, and so I'll talk more about this tomorrow, but you basically have to choose like what are galaxies, what are potential host galaxies to gravitational wave events. So in here, that's being summarized with the luminosity limit, the B band luminosity, at which like we're including galaxies down to. So like this includes galaxies as faint as 0.01 L star in the B band, and then in the orange dashed line is galaxies that are relatively brighter than 0.626 L star. And so you can see there is some difference that happens depending on what luminosity threshold you pick. But for the most part, these are all very similar and also very similar to the case where we just use one host galaxy. And that's because when we're including all those other potential host galaxies, they tend to just be at that same redshift anyway because of large scale structure. And so in this case, we get an exceptionally informative measurement of the Hubble constant. I should finish up soon, but here is what the statement that I said before, where if we have a counterpart, the convergence at the 1 sigma level of the Hubble constant is roughly 15% over square root number of events, where it is much slower if we don't have a unique host galaxy. And this is also an extremely optimistic number, this 40% over root n. I can also show you all this movie that shows how the convergence happens in the statistical dark siren method versus the counterpart method. So these different colored lines that get added are individual events. And you can see that in the counterpart case, they're like very peaky because there's just one redshift, where in the statistical case, they are sometimes kind of peaky, but tend to mostly be much flatter because we have a lot of different galaxies that we're marginalizing over. And they do both converge somewhat to the Hubble constant that was simulated, which is here 70 kilometer per second per megaparsecs. And the statistical one is much slower. And yeah, again, for the most part, like if we're using mostly binary black holes, they tend to be further away, more poorly localized, because further away corresponds to bigger localization volumes, more potential host galaxies. The vast majority of events are actually going to be completely uninformative, or worse, bias your measurement if you include them. So you really just want to look at like the best localized events for this method. And I'll talk more about that tomorrow. But just to quickly explain what spectral sirens are, and again, I will talk more tomorrow, but just to like give you a little hint in the last minute, that's when we actually use the only gravitational waves and look at the detector frame masses versus distance, where the detector frame mass is just the redshifted mass. So it's mass times 1 plus redshift. And we essentially use the fact that things at higher mergers coming from higher distance have higher redshifts, and therefore they appear more massive. And we like use the shape of this distribution to simultaneously infer what the source frame mass distribution is, and what the relation between distance and redshift is, or cosmology. And so I guess I will just talk more about that tomorrow, but yeah, I guess another thing to point out is that I've only been showing the Hubble constant, but higher order terms are going to matter. So it's not just this is kind of a funny way of that I chose to show it, but the full Hubble parameter as a function of redshift divided by the Hubble constant versus redshift. So you can see it's not just a linear relation. I mean, the distance redshift relation is not just linear. And this just gives you a sense of where we're actually going to be observing events. So a lot of the binary black holes that we observe are actually at redshift 1 and beyond, where the redshift distance relation is not just driven by the Hubble constant. So if we can also try to infer like omega matter, and especially dark energy equation of state. And then especially when we talk about the next generation ground-based detectors, that will get us all the way out to the very edge of the mergers that happen in our universe. So this shows like where we think binary neutron stars happen in redshift space, where we think binary black holes could happen in redshift space, versus like the horizons for those are these different lines here. So with like these proposed next generation detectors, Cosmic Explorer and Einstein telescope, we would actually observe, we would be sensitive to binary black holes out to like redshift 30 and beyond, where we don't actually think that any astrophysical black holes happen. And so, yeah, just to summarize today, and I'll go into more detail tomorrow, but gravitational waves encode the distance to the merger, and we can learn the redshift from host galaxies. And we have a unique host galaxy if we have a counterpart that's called a bright siren, or possibly in like very, very loud, well-localized events, we might have a unique host galaxy just from the gravitational wave localization. For even otherwise, even for like our loudest events with the best localizations, there's going to be a bunch of potential galaxies there. And so we can marginalize over them. That's called dark statistical sirens. And then features in the source frame mass distribution, spectral sirens. And yeah, those are all my slides for today. So I guess we should take a break, but I'm happy to answer any questions during the break or on Slack or whatever.
Shall we take a break and then we can ask questions on Slack and elsewhere?
Okay, yeah.
Half an hour break.